We now have a double presentation from Tom Butcher and Ryan Rogers. So Dr. Thomas Butcher is the Technical Director of NORA, the National Oil Heat Research Alliance, and he has a very long history of research work on energy systems, air pollutant emissions, and the use of biofuels in boilers and furnaces.
Okay, I'm going to talk about a rather different fuel, ethyl levulinate. Klaus talked about the wide range of fuels that are under consideration. I found that really fascinating. This is maybe yet another one. We have been working on this for quite a while, and I'm going to share with you not so much discussion of the production of this fuel, but rather more on the potential and use of this fuel for home heating systems. So just a little bit about ethyl levulinate. It is derived from wood waste from biomass. It is a cellulosic fuel. Mild acid hydrolysis is the first step, leading to levulinic acid, which is esterified into the production of ethyl levulinate. So ethyl levulinate is a relatively short molecule. It's a C7, but it has a high flash point, which makes it potentially usable for the home heating market. Little bit of the property overview. It's a heavily oxygenated fuel, and so the heating value is about 31% less than petroleum number 2. Good lubricity, good viscosity on the low side. I would say the cloud point of this fuel is extremely low, which is part of the reason why it has gotten so much attention in the northern part of the US, where there is concern about petroleum diesel and biodiesel under cold climate conditions. Density a little bit higher than that of water. It is very water miscible. Measurements have indicated a high oxidation reserve, although although tests are still underway on the question of long-term storage stability. Low acid number as a new or as delivered fuel. So it looks pretty good. We have explored many different aspects of EL as potential use in the heating fuel. So first of all, starting with blending with petroleum number 2 fuel oil, not great. We have done field tests in Maine at blends up to 10%. For a couple of heating seasons, looks quite good, but once you go above that, it will separate from petroleum number 2, even at room temperature over 20%. So that's clearly a strong limitation. Blending with biodiesel is possible. It does not separate. We have done a lot of work in this area, thinking that biodiesel could be used as a way to extend the available supplies of ethyl levulinate in the future. It improves the cloud point, but not maybe by as much as you would assume based upon kind of a linear average between biodiesel and ethyl levulinate. So it's really only going to gain a few degrees C in cloud point. So not enough to really solve the low temperature flow problem for biodiesel. It will lower the acid number and increase the oxidation reserve a little bit. So it's not a huge impact in that particular case. We explored blends of biodiesel, petroleum number 2, and EL. Looks like it is potentially attractive, although blends of that type are still driven by the cloud point of the biodiesel. And so you still have the biodiesel cloud point question. We went down that pathway. We did a lot of work in that area, not long pursuit. It's not ongoing as a future potential for now. Combustion, long-term storage of blends with EL and biodiesel look good. We've done a lot of combustion testing, looks fine. I'll talk more about that. Elastomer swell is not good. The standard elastomers that are used in petroleum systems, Viton, nitrile, swell significantly with EL blends. We have done a lot of work and looking at different options for elastomers that could be considered for use with EL, and I think made some very significant progress. Teflon is certainly one of them. Silicon, other forms of Teflon have looked, fluorinated elastomers look quite good. So a summary of the good and the bad. It has extremely good low flow properties, stable, derived from wood waste, which is great. Outstanding greenhouse gas scores. I'm going to show something on that. Blends well with biodiesel, and it has very low NOx emissions. Bad, separates from petroleum diesel. It is not compatible with common heating system elastomers, which is a major concern. It freely absorbs water. We have that listed as a bad attribute, although we're not quite sure that that is going to strongly affect us depending upon how this is implemented. And it's not yet produced in quantity. So I'll talk a little bit in the end about that. I just want to kind of wrap up with some before I turn it over to Ryan, with some discussion of the greenhouse gas scores. So this is showing greenhouse gas emissions for the delivered heat with a conventional or non-condensing boiler. In the US, conventional would be condensing, I guess, in the EU. So if I look at kilograms of CO2 per equivalent million BTUs that are delivered, starting at the bottom, ultra low sulfur diesel or conventional heating oil, quite high, biodiesel. And then if we go to the EL from different sources, we actually get into a negative greenhouse gas emission score because of the co-products that are produced in the production process for EL. And that's part of the reason that we are excited about this. So from here, Ryan Rogers is going to take over. And I just want to say a couple of words about Ryan. We worked with the Dead River Company, which is a major leader in the state of Maine in fuel distribution and heating systems. And Ryan has been incredible in terms of the initiative that he has taken to get this to work in a practical sense. And Ryan's going to talk about his experience. So Ryan.
Air pollutant emissions and the use of biofuels in boilers and furnaces. Ryan, for his side, started in mechanical construction, and for the past 6 years, he has been general manager for Dead River Company. He has managed retail fuel operations in Maine, and the cold climate over there provided plenty of opportunities to test EL. And I will now leave the floor to Tom, I think, who will start to explain what is EL.
Morning, good afternoon for those of you that are overseas. Yeah, I got brought on to this project. I was very excited. You know, the cold flow properties of this fuel got me very excited. The fact that it can be produced from forest, residual waste, and lots of different from cellulosic waste got me very excited. The area I live on the Canadian border, very close, very almost, well, the northernmost city in the state of Maine. And so cold flow is a huge issue for us, even with heating oil sometimes. So I was very excited to take this project on, and our task was to prove, can we burn this? We started out at the University of Maine at Orono. We partnered with the university. They chose my market, I believe, because we go through about 10,000 degree days a year, 9 to 10,000. So we have plenty of opportunity to test out heating fuels up here. Also for the mechanical acumen of myself and my team. We started with fuel pumps that could be bought, in America, in Europe, and just everything failed. and we learned a lot from it. We ended up going to a Danfoss Beckett pump, and we kind of had to take a step back and look at. I worked with NORA, and we looked at what pumps have a simplistic design that we could make this fuel work well with. The pump that was chosen ended up being the Beckett Danfoss. Next slide, Phil. What we had to do was, after we kind of tried to seek out what we could buy and that wasn't working, we started to do a lot of elastomer testing. NORA started testing elastomers of lots of different types, and we found 3 that worked, that we got really excited about, and we started replacing those seals, and you can see that inside of a fuel pump we've got many components. The picture on the left is full of nitrile and Viton, and then the picture in the center have got some replacement parts, some that I'll talk about shortly. So we finally got to a point where we were able to burn the fuel. Things were sealed. We didn't have any leaks, any failures, and we. The other interesting issue that we had was the spectrum of light. It's a blue flame. It's unlike traditional number 2 heating oil. We were having lots of issues with keeping the CAD cell primary on, and we wanted to try to take an existing fuel oil burner and burn EL through it. So I'll go back a little bit, Tom. So one of the main issues with the pump that we had was the pressure regulator. In the picture on the right, you'll see the furthest right is what the Beckett Danfoss comes with, that pressure regulator, and you can see the Teflon and brass pieces that a friend of mine machined. That little piece of nitrile would swell and close the oil off, and we'd have a flame failure. Which the reason this pump was a lot better, because we didn't have leaks. We actually had 0 fuel to the burner. The development of these pressure regulators allowed us to burn the fuel successfully. The interesting thing that we noted was the air reduction. We actually ended up having to almost close the air off, which in turn brings your stack temperatures down a little bit. And the traditional oil burner, the chassis was sized for air to the burner. Well, with this fuel, one thing we realized is that you're limited by basically the fuel system. So, next slide. So we took everything that we learned along the way at UMPI. We got a successful package together, and I wanted to test it a little bit more closely. We also wanted to find out what happened when you took my tank was 20 years old. It was a number 2 heating oil tank. We wanted to know what happened with sludge and EL. So we literally pumped my oil tank out to empty and filled my oil tank up with EL, and I took tests along the way. The picture in the center was the first bit of oil that came out, and the picture to the very right actually surprised us. We thought we were going to have clogged filters. We thought we were going to have sludge issues. And as you can see, um, none of that occurred. Another advancement that we made in we wanted to test at my house was on the picture all the way to the left, just after the filter, there's a fuel shutoff. The Firematic valves that you currently buy today are full of nitrile, and those pose a problem. We found some Firematic valves that did not contain nitrile, and we wanted to test those as well. The next slide. And as you can see, as the weeks went on, the fuel kept getting clearer and clearer. The filters became cleaner and cleaner. And one thing I was very amazed at is how clean this fuel burns. I noticed that really not a lot of buildup. In my boiler, it brought my stack temperature down almost 200 degrees because of the air reduction. And a lot of the issues that we were anticipating did not occur. The fuel burned extremely well. Next slide. The other issue that we had as we're leading towards the path towards a commercialized type of a setup was the photodiode that we originally used at UMPI could not. It was really one of the only ones that we could get our hands on. Tom had a great idea of using resistors in parallel. So instead of the control going from 0 to infinity, we brought our control from 0 to 10,000 ohms. That allowed the existing primary control and CAD cell I to be used. And during the entire, I burned the entire 275, which is right around 240 gallons. During that entire time, I experienced no failures, very good efficiency, and the resistors in parallel really allowed us to take a existing controls burner and allow this fuel to be burned through it. One thing that we're looking for is, we through this process we proved that it can be done. It can be burned. What as we kind of move forward, what we're really looking for is some help from people that build burners and build parts and pieces to actually help us in coming up, commercializing this. I think what we've learned is how to put together a proof of concept burner for future fuels, and this project was a lot of fun, and we continue to make progress currently every day with this.
Ryan, thanks. Let me just chip in with a couple more things before we wrap up. We made a decision along the way to use EL 100, that is 100% EL, as opposed to a blend, as our fuel of choice. That was a carefully planned, thought out decision, and it seemed to work well. You have to change the elastomers anyway. Silicon as an elastomer works well. We have also developed a composite Teflon graphite lip seal which we've started to test with and seems to really work well. That's an area that we had concerned about. Next steps include a larger commercial burner, which we have completed the conversion of to EL, and we'll be doing some large scale testing with that. We are working with a fuel-fired heat pump as a totally renewable future solution. That's a project that's underway. And we need the fuel. So the first production plant is underway, at least the design development of it, by Biofine Development Northeast, which is the owner of the technology and the folks who are going to push this forward. I don't know if we have time for questions, but I'd be happy to. We'd be happy to.
Thank you very much to you two. I have a question. Are you aware of similar experiences in other states or countries?
I'm not aware of other efforts to look at EL as a heating fuel. There has been considerable effort to look at EL as a possible engine fuel.
All right, thank you. We have a question from the audience asking if it is implied that plants that live in colder conditions and get turned into some form of biofuel and renewable fuel will have better cold flow characteristics. Would one of the panelists like to answer that one?
This fuel has good cold flow conditions. Temperatures in Maine can easily reach negative 10, 20 degree F regions. Tanks should always be inside, but they're not always. It's a big concern for biofuels in general in northern climates. And this is a solution. I hope I answered that question.
Alexander, you want to jump in?
Yeah, as I was referring to a bit in my presentation, I didn't go into the technical details. HVO, as with a synthetic fuel, you can actually set the cold flow properties quite more easily than with other fuels. It takes a little bit of effort and makes it more expensive, but I can't do the calculation off the back of my head. It's around below 0 degrees Fahrenheit. So we're around minus 27 centigrade up to minus 35 centigrade. That's the cold flow properties that you can get with HVO. But not every HVO can do that. That is clear. It needs a commitment from the producers. So these quantities will be limited around the globe, but there is a solution from the same feedstock and the same type.
Alexander, thank you. We have seen that data for HVO. It looks quite interesting. You know, it's going to be a question of what comes to the market.
Well, we have several different qualities because we work in different markets. We have a quality that you can freeze in your normal freezer at home, and we have quality that is Arctic quality that will go up to minus 35. That really depends on the contracts and who you're talking to. But we guarantee minus 22 centigrade, which for any diesel is already quite good. So it is possible, and there's little that you can do with additives. So it really depends. Yeah. You're always going to pay a premium, so the product is not going to be available to everyone everywhere around the globe.
Yeah, okay.